In Lab 8, Experiment 2, Cold Packs versus Hand Warmers, we want to explore the concept of heat of reaction in a little bit more detail. First of all, let's define what we mean when we say heat of reaction. Heat of reaction is the amount of heat absorbed or released during a reaction. It is the difference in energy between the breaking the bonds in a the difference in energy of breaking the bonds in a reactants and forming the bonds in the products. We give heat of reaction a special symbol. When that heat of reaction occurs at a constant pressure, we refer to that heat of reaction by the symbol delta H, and very formally we'll call it the change in enthalpy. Let's take a look at a very simple and common exothermic reaction. Now wait a second, what is an exothermic reaction? An exothermic reaction is a reaction where the energy of the reactants is greater than the energy of the products, and heat is released along with the products. In these scenarios, the heat of reaction has a negative sign. Let's take a look at a specific example. My favorite example, and I do it every Halloween, is I like to fill pumpkins with acetylene gas. Oh, by the way, this is insanely dangerous. Don't do this under any circumstances. And I'm not just saying that, I mean really, I'm stupid to do this. You have acetylene gas, combine it with oxygen, and notice that I do it in very, very controlled environments here. Maybe I shouldn't show you this video at all. When you react acetylene gas with oxygen, you get carbon dioxide, water, and 1,301 kilojoules of energy. All right, so let's take a look at the reaction in progress here.
Okay, this is a class activity. It's the generation of acetylene gas and then the ignition.
Oh, that was too awesome. Let's see it again.
Okay, this is a class activity. It's the generation of acetylene gas and then the ignition.
All right, one more time,
Okay, this is a class activity. It's the generation of acetylene gas and then the ignition.
I can never do that too many times. All right. So when we observed the heat energy, we were observing an exothermic reaction. Why? Because we saw the energy being produced. If we had put our hands near that pumpkin, they would have felt hot, right? Matter of fact, they would have gotten very badly burned. I know, as I said, it's stupid to do this. You could have had the pumpkin literally explode, pieces hurt. You'll notice I did it inside to protect. Don't do this. But I digress. Since energy can't be created or destroyed, where did the energy that we observed come from? Remember, energy can't be created or destroyed. So if we released 1,310 kilojoules of energy, where did it come from? Where did the energy produced come from? It came from inside the chemicals. Specifically, well, we'll just say it came from inside the chemicals. It came from inside the acetylene and the oxygen gas. Because it released energy from the inside, the resulting chemicals formed had less energy than the starting materials. If you wanted to, after putting the word pumpkin on your paper, if you wanted to, you could draw an energy diagram. An energy diagram is a way of graphically illustrating what occurs during a reaction. You have reaction progress, in other words, time on this axis. Then you have energy, and this is the energy of the system. In other words, the energy of just the chemicals involved. We start off our reaction. We have acetylene gas, and we have oxygen. And they have some energy inside those chemicals. I then add my barbecue lighter to it. That causes the energy of the system to increase. It also provides what's known as activation energy. That's the energy needed to start a reaction. Then the reaction occurs, and it produces carbon dioxide and water. And carbon dioxide and water have less energy inside their bonds than does the acetylene and oxygen. So the height difference between those two would actually be equal to 3,100 kilojoules. So in an exothermic reaction, like we witnessed, the chemicals have less energy than the reactants. However, because we're part of the surroundings, not the system, but because we're part of the surroundings, we refer to the reaction as producing energy, because this reaction frees energy up from inside these molecules to us so that we can use them. But it actually costs the chemicals themselves. Remember, as chemists, we always divide the entire universe into two parts. We divide the entire universe into the system, in this case the acetylene and the oxygen, and everything else. And we call everything else, or everything that's in contact, with the system, we refer to that as the surroundings. And we made great use of that concept in the last lab. We know if I use the flame produced, the fire produced, I can't draw fire apparently. What in the world is that? Okay, I'm going to quit while I'm ahead. Let's say I use the fire produced by my system to heat some water. My water would get hot. Exothermic reactions always feel hot to an observer. Exothermic reactions always feel hot to an observer. The opposite of an exothermic reaction is an endothermic reaction. In an endothermic reaction, the energy of the reactants is higher than the energy of the products. Heat is absorbed and used to convert the products products. So let's take a look. In this scenario, they're giving us the reaction of nitrogen and oxygen. In order to get them to form nitrogen monoxide, you have to add 180 kilojoules of energy. If we were to do our energy diagram of it, we'd start off and we'd have nitrogen and our oxygen. We'd have to add some extra activation energy to get the reaction started, and then we'd form our products. We're adding energy to the system not just to get it going. It has some activation energy. But we're also adding energy into the chemicals themselves. Why? Because the chemical bonds in our nitrogen monoxide store more energy than the bonds in the nitrogen and the oxygen do. So in order to get them to form this compound, we have to add energy to our system. Now the question is, where does this energy come from? After all, energy can't be created or destroyed. So if I have a bunch of nitrogen and a bunch of oxygen in a metal cup, and I'm holding it in my hand, oh wow, my artwork is lousy, and I have it in my hand, is this going to feel hot or cold to me? Well, energy can't be created or destroyed, so in order for my system to gain energy, my surroundings have to lose it. So heat would actually flow from my hand into my cup there. So an endothermic reaction feels cold to the touch because the reaction is actually taking energy from us in order to make the reaction go. Pumpkin. Put pumpkin on your paper. Pumpkin. Put pumpkin on your paper. Real quickly, in an endothermic reaction, energy is a reactant. In an exothermic reaction, energy is a product. So this would be an exothermic reaction because energy is on the product side. This would be an endothermic reaction because energy is on the reactant side. This would be an exothermic reaction because our energy in the form of heat is on the product side. Just as a quick summary, in an endothermic reaction, heat is absorbed, and heat's going to be a reactant. In an exothermic reaction, heat is released, and heat's going to be a product. I'm going to add another level to that chart here. I'm going to add feels. As an observer, an endothermic reaction feels cold to the touch. In an exothermic reaction, it feels hot to the touch. In today's lab, it's important that you remember the water is the surroundings, not the system. In other words, for an endothermic reaction, water is going to cool down. For an exothermic reaction, the water, because it's part of the surroundings, will heat up. And that's all the help I'm really going to give you with today's lab. That's it. Beep.